Okay, welcome back. This is COL 774 machine learning, and today is Friday, April 17, 2020. So, last class we looked at GMMs, that is Gaussian mixture models, right? And remember that they were sort of generalization, if you will, of GDA to the case when i's are present, right? So this was sort of the diagram that we had, and this is the setting xi I equal to 1 to m, right? And this data is being generated from a set of, let's say, k clusters, right? And in this picture on the left, we are representing these k clusters by these set of points here. Okay, and right, each cluster comes with its own set of parameters, let's say mu1, sigma1, and mu2, sigma2, right? And we assumed that there is sort of a generative model where we generate zi using the multinomial distribution based on some phi parameters, where p l is equal to 1, l equal to 1 to k, and we also have xi given zi equal to l comes from a normal distribution with parameters mu l and sigma l, right? This is for all l, right? And sort of the key difference from GDA is that these zi's are unknown or missing, right? And this is what really makes this process sort of interesting, that we don't know the i's, and we, right, which is sort of the cluster labels, and we also don't know what these theta parameters are, right? So we also want to figure out what the set of parameters are, which is phi, mu l, sigma l, l equal to 1 to, right? And given this setting, we said that okay, we can actually solve this problem by a two-step process, which was a combination of this e step, which was which would ask us to estimate p of zi given xi parameterized by theta, right? So given the current set of parameters, we would estimate these zi's, right? And these are essentially soft assignments, right? So we will not sort of get a hard assignment of any point to a given cluster, but we will only get probabilities which will tell us sort of its proportion that belongs to a given cluster, right? And all these p of zi's will add up to 1. And in the second step, right, and this first step, each step would be estimating these zi's given the current set of parameters, right? And the m step would then sort of improve over these thetas, right, given the zi's. So the m step would essentially be argmax over theta of p of xi, let me write it here, zi, and then parameterized by theta, right? And this is we can write this is over all examples, right? So this is our expression for M step, right? And right, what is really interesting is that right, we sort of said that uh, that an iterative, right, or sort of alternate sort of this E and M step would converge to something interesting, right, which will not only give us the cluster assignments zi's, right, which again will be soft, but also the sort of the parameters, right? And in this class we will actually try to formalize this notion. Just one quick remark here. I have written argmax theta product over this p xi zi parameterized by theta, but of course you will take a log of this equivalently and then maximize over that quantity. And one final remark before we go to the next slide I want to make here is that both this E step and M step are tractable, right? So if we know the parameters, then we know how to estimate P of Zi given xi parameterized by theta. That is almost like prediction in case of GDA, right? Right, and we looked at the expression for that in the last class. Similarly, if we knew what zi's are, then we can estimate theta parameters, and again that is again very similar to estimating parameters of GDA, because now we are working with a given cluster assignment, right? And then we sort of iteratively repeat this process. And today's class will essentially generalize this to a more general idea of what we refer to as expectation maximization, or the EM algorithm. Okay. Before we go to the EM algorithm, there are few remarks that I want to make, which is about connection between the GMM Gaussian mixture models and the k-means algorithm, right? Which is as follows: that k-means, in fact, is a special case of GMM under the following conditions, right? So first, right, in GMM, if we make ZIs to be hard assignments, right? Which means that assign a point to the cluster L such that P of Zi equal to L given xi theta is maximized, right? So in the E step, right, this is the E step. Is in the E step, right, in GMM, instead of doing the soft assignment, right, you assign each point to that cluster for which this probability of Zi equal to L given the point and parameterized by current set of parameters is maximized, right? So instead of doing a soft assignment, you do a hard assignment, and second, fix each of the covariance matrices to be diagonal, right, for all L, right? And this is sort of the right. This is in the this is part of the parameter estimation or the MSTEP, right? This is part of MSTEP, right? In some sense, we are not even estimating the sigma L, the covariance matrices. We are just fixing them to I, right? So if we really make these two assumptions, then we can show that GMM reduces to our plain old k-means, right? So in some sense, right, and this is homework for you to be able to prove this, to show, right? And this is not very difficult, right? So I'll encourage you to go back and think about it, why this is the case, right? But this makes an interesting point that our idea of doing this sort of E and M step where these ZIs are soft assignment is essentially generalizing something that we have seen before, which is doing this with with hard assignments in the context of emails. Okay, let's move forward now to our exposition of expectation maximization. Let's come to EM algorithm, which is expectation maximization, right? And this is based on a paper by Dempster et al. Back in 1977, right? And it is one of the very important and very popular algorithm in machine learning to deal with the problem of missing data. Right, and we will actually describe this algorithm in a fairly general setting, and we'll see that it actually generalizes what we have seen before in terms of GMM and also k-means. Okay, so what is the setting? The setting is very simple, that you are given a bunch of data points, xi I equal to 1 to m, right? These are your, this is set of data points where each xi belongs to some real space, let's say n-dimensional Euclidean space, right? And we will assume that there is an underlying model for generating this data, which is as follows, right? So this data is generated from some underlying distribution, which is given by this p theta uh, right, and which essentially is parameterized by these theta parameters, right? So this xi zi is being drawn from this underlying distribution, right, parameterized by theta, where these zi's are unknown to us, right? Right. uh, Other way to think about this generative process is that there is a world out there, right, which samples from this underlying distribution, right, these theta parameters, and these theta parameters could be sort of fairly general, and these xi zi samples are generated one by one, but these zi's are removed from what you observe, right? So we do not observe these zi's, right? And what is given to you is only these xi's. And in general, right, the different kind of information could be missing for different data points, right? Although we have seen the case of GMM where the specific yi's, the class labels are missing, um, right, and we are only given sort of the points, but in general, right, you could sort of generalize this formulation where different kinds of information is missing for each point, but uh, let's not worry about that as such at this juncture. Okay, so then what is the objective? The objective of this problem, uh, right, or objective that we are interested in is not really very different from what we have seen before. We would like to essentially um, estimate theta parameters, which, let's say, maximize the likelihood of observed data, right? So this is our, and we'll move on to the next. Okay, so what is our objective? Our objective is to find these parameters, right, theta parameters, and we are not committing to a specific form of probability of data, right, given or parameterized by theta, which is sort of equivalent to to finding these theta parameters, right, which maximize the log probability of data parameterized by, right? But what is important in this setting is to really answer the question that, what is this probability over? What is our data, right? And a careful sort of thinking will tell us that our data is exactly the set of points that we observe, right? And in particular, right, and this is in contrast to supervised standard supervised learning, that there is no sort of ZIs here, right? So there is no ZIs, right, right, in this expression, because we don't really observe them, right? So what we can really maximize is probability of the data that we observe, which is, argmax theta, right, log of the probability of observing all the data points, and assuming that they are generated independently from the underlying distribution. This is simply xi parameterized by theta, right? And this is the key, right? This is in fact the key difference, and also the key challenge, that this maximization is over the likelihood, right, which is over the observed data points, right, observed information, right, which is just the data point, right? So there is no sort of zi or no class labels, if you will, in this case, right? And we want to maximize this, right? And this is a really important point, that we have to sort of keep in mind, right, as we do this EM algorithm, right? So given this, right, now the question is, how do we do this? Right? You could say that, fine, this is okay. We right, we could try to maximize this using something like gradient ascent, right? And let's see what happens. Right. So let us write this expression argmax over theta log of I equal to 1 to m p of xi parameterized by theta, and we can take sort of the log inside this product. So this becomes argmax over theta sum over I equal to 1 to m log of p of xi parameterized by theta. So this is fine. But now the question is, right, what is the expression of log of p of xi parameterized by theta, right? And these are essentially also can be thought of as marginal probability of the data points xi, right? And the challenge here is that we do not have an explicit form for this pxi parameterized by theta, but what we have essentially, let me write in a different pen, is we have p of xi zi parameterized by theta, right? So this is what we have, but we want to compute this p of xi theta, and you would say that, okay, that's not very difficult. We can equivalently write this expression as log of p of xi zi theta, and then we could simply sum over all the assignments of these zi variables, right? And I'm right. This is sum over zi is assuming zi's take discrete values, but otherwise, if it is continuous, it will be an integral, right? And this is sum over all examples, and then take uh, sort of argmax over this expression, right? So we could try to maximize this with respect to theta parameter, right? So this is fine, right? In principle, you could actually do it, but the problem here is really this right. Let me write here. The problem here is this sum. Not clutter this too much. Uh, Okay, so I changed the last slide too quickly. So let me write the expression again that we were talking about. and this is pxi zi parameterized by theta. Then we have sum over zi's, right? Because we are marginalizing over them. Then we have a log of this expression, and then sum over all possible examples, right? And we want to essentially do argmax over this argmax of this expression with respect to theta, right? So this is essentially our estimate of maximum likelihood parameters in this case. But really, the challenge that we have is this quantity, right? This is the problem, which is the sum inside the log, right? And this sum inside the log uh, is a problem because this does not factorize, right, into a more simpler form. And in general, right, sort of computing the gradients of this can be sort of intractable, or computationally quite challenging, right? And this is the problem that we really want to solve. And right, and how did we really solve this in case of GMMs? Is we made this sort of assumption that we could do this using a two-step process, that if we really knew, right, thetas, right, then we could estimate zi's, right? So if someone gave us the parameters, then we could estimate zi's, right? And if, on the other hand, if we knew the zi's, right, then we could estimate the thetas. And right, and these, both these steps, right, at least in the case of GMM, were actually tractable, right? They were computationally very efficient, right? So when I say intractable, here you just used it maybe a little bit loosely. I've not exactly defined, the notion of intractability, but let's say this is, computationally difficult, right? And in case of GMM, we could show that both these steps were in fact tractable, right, computationally very efficient, right? If we knew the thetas, we could estimate zi's, and if we knew the zi's, we could estimate the thetas, right? And then we had this two sort of iterative process, uh, right, which repeated these E and M steps, right? And note that this is this is helpful, because especially in the E step, once we estimate zi's, right, then we can quote unquote sort of fill in zi's, right, right, and essentially get rid of this sum, right? This is the key idea. But now the question is, right, what is the mathematical basis of this E M step based computation? Right, I mean, is it just sort of heuristic that over a certain number of iterations, right, we estimate the parameters, then estimate zi's, and then estimate the parameters again, and I mean, does this process even converge, and does it converge to something meaningful, right? These will be the sort of the questions that we'll try to answer as we talk about the EM algorithm, right, the expectation maximization algorithm. And in the process, we will show that it is not only the case that it actually converges to something meaningful, but also sort of generalizes beyond just Gaussian mixer models. And let's look at that in the next slide. Okay, so before we go to the exposition of the EM algorithm, let me take a detour into describing something that will be important for us, which is called the Jensen's inequality. Okay, and right, to state this Jensen's inequality, let us come back to the notion of convex and the concave functions. So recall that suppose there is a function fx, right, defined over some n-dimensional space, right? In this case, this is just x belongs to R, uh, right? Then what was the definition of, right? This is x1 and this is x2, and our definition of convexity was simply that the function lies below the line joining any 2 points on the curve of the function, right? So which mathematically would mean that f of alpha x1 plus 1 minus alpha x2 is less than equal to alpha fx1 plus 1 minus alpha fx2. Okay, where x1 and x2 are some points in the domain, and right, this alpha is between 0 and 1. Okay, and similarly we defined the concave function, right, where we had this is x1, this is x2, and here the function lies above the line joining any 2 points, and we had f of alpha x1 plus 1 minus alpha x2 is greater than equal to alpha fx1 plus 1 minus alpha fx2. Okay, uh, and this is essentially fx. Okay, so let me draw that curve again. So this was our convex function that we were dealing with, right? And this is some point x1 here, this is x2 here, right? This is f of x1, and this is f of x2, right? And the the definition of convex function states that f of alpha x1 plus 1 minus alpha x2 is less than equal to alpha f of x1 plus 1 minus alpha f of x2, right? So this is the definition of convexity, where alpha is between 0 and 1, and we stated that on the previous slide. Now Jensen's inequality states the following, right? So it also needs distribution, right? P over this domain of x, a domain of f, which we denote by this curly x, which is Rn, right? So note that in the above sort of setting, although in the diagram we are dealing with just one-dimensional input in general, right? This each of these x belongs to this Rn space, right? So either it is the entire sort of Euclidean space in n dimension, or it could be sort of a continuous bounded subset of it, right? So given this distribution, right, this p of x, right, is a probability distribution, right, where each x belongs to this curly x, or essentially in our case Rn. Jensen's inequality states that if I take the if I take function f applied over expected value of x, then this quantity is going to be less than equal to if I take expected value of the function f itself, right? So the LHS is essentially the function f evaluated at the expected value of x, and the RHS, the right hand side, is the expected value of the function f itself, right? And both are taken with respect to this distribution p of x, and it could be sort of any distribution over x, right? And I will not go in sort of the complete proof of this over the complete proof of this, but intuitively, right, the the intuition behind this inequality is the right hand side, right? So this RHS is you know in some sense, is the area under the curve f, right? And this is little loose because right, this is actually the area only if this is a sort of a uniform distribution, right? So assuming that px is uniform, then this is exactly the area under this curve, right? And on the other hand, so this will be sort of this shaded portion, right, if you will, right, under the uniform distribution. And the left hand side is f evaluated at expected value of x, right? And again, under sort of the uniform distribution, right, you can show that this is nothing but area under this green curve, right, which is sort of the midpoint of x1 plus x2 by right? So under the uniform distribution, right, the f evaluated at the expected value of x, which will be sort of the middle point between x1 and x2, and this f of expected value of x is nothing um, but area under this green line, right? And which is clearly less than the area under the curve, right? And this is again sort of just the intuition, right? And I'll encourage you to sort of right, if you're interested, I could post additional links about the proof of Jensen's inequality. And this is a very important inequality, right, when we do deal with especially advanced set of topics in machine learning. Okay, and so this is fine, right? We will use this, but we will use an additional property here of Jensen's inequality, which states that that this is fine, this holds for any convex function, but if f is strictly convex, right? If f is strictly convex, remember, if f is strictly convex, then this inequality, this sort of less than equal to, becomes strictly less than, assuming x1 is not equal to x, right? And alpha is strictly between 0 and 1. So for such f where f is strictly convex, right, the above inequality, right, which is essentially the inequality in this Jensen's inequality, is equality if and only if, right, either of these two conditions are satisfied. So the first condition is either you know uh, the p assigns all the mass, all the probability mass to a single point, or, right, which actually is more important for us, right, we will use, is that f is a constant function, right? So once again, what are we saying? We are saying that we stated this Jensen's inequality where this is our LHS and this is our RHS, right? That f of expected value of x under this distribution p is less than equal to expected value of x under p, right? And we are interested in figuring out when does this inequality becomes equality, right? And assuming that f is strictly convex, right? So if f is strictly convex, then this inequality becomes equality only in cases where either p essentially collapses to single point, right? So if all the probability mass is at a single point, then clearly, right, it's not very difficult to show that this actually becomes equality. But the second case, which is sort of more interesting for us, is that suppose p is not right, something which assigns all the mass to a single point, but p is some general distribution, then you know Even then, right, or then if f is a constant function, right, if f of x is some constant c, then again, right, it is not very difficult to see that right, this again will become an equality, right. If f is a constant function c, then LHS will be f of expected value of x, which is c, and RHS will also be expected value of fx, which is c. So both the sides will be c, right? And this is if and only if I have only proved it in the in one direction, but I guess you could also prove it in the other direction. Um, so let me just quickly state, the previous inequality in the context of concave functions, which actually is what we will use. This is x1 and this is x2, and this is f of x. And for concave functions, we have f of alpha x1 plus 1 minus alpha x2 is now greater than equal to, right, the function lies above the line joining any 2 points, alpha x1 plus 1 minus alpha x2, and this is a strict inequality for concave functions, and x1 is not equal to x2, and alpha is strictly between 0 and 1. Okay, and then the Jensen's inequality for concave functions is again, we are given a distribution p over the entire sort of domain of uh, f, and Jensen's inequality now states that f of expected value of x is now greater than equal to expected value of x, right. Right, so it's the same inequality, but this is the direction is reversed, and if f is strictly concave, then above becomes an equality if and only if either p collapses to single point, right, this distribution px collapses to single point, or f is a constant function, right. So if either of these two hold, then this becomes a strict equality, and this is exactly what we will use for our work. Okay, so let's keep going. Right, so for our problem, right, remember now we wanted to compute this expression argmax of theta sum over all examples log of sum over zi's p of xi zi parameterized by theta, right, and this was over log likelihood, right, which we will also denote by ll theta. In fact, this entire expression, right, not just till here, but sort of the entire expression is the log likelihood, right, and what we are really interested in in some sense maybe figuring out then if we can sort of get rid of this sum inside this log, right, and right, so 2 points here, right, which will be helpful for us. So one is that log is a strictly concave function, right, and just to sort of remind you, the graph for log x, right, crosses the x-axis at uh, uh, right, crosses sorry, uh, Yeah, the crosses the x-axis at x equal to 1, right? So this is 0 at x equal to 1, and it sort of goes to minus infinity as x goes to 0, and goes to infinity as x increases, right? So this is log of x. Uh, okay, and right, therefore this is strictly concave, right? So this is fine. And if you think about Jensen's inequality, right, that is exactly what will apply, right? So thinking of your log as your f function, right, what we have inside this expression is right, we are looking to get an expectation inside, because if we could get it into the form of f of expected value of x, then we could sort of interchange this f and expectation, right, to get this expectation out of the log function, right? But now the question is, right, that how do we really get an expectation, right? So this sum zi gives us an idea that maybe there is an expectation sitting out there inside this expression, and to really convert this in the form of an expectation, we'll do a mathematical trick, which is, we will define, right, qi zi as sort of some distribution over zi's, right? And for now, right, this is, let's say, assume that this is sort of non-zero at every point zi, right? So we'll define this distribution qi zi, right, which is some distribution, different distributions for different zi's, right? We've just defined them, right? I guess out of nowhere, but we'll see why this is helpful for us. And then let us look at this expression, which is log of sum over zi pxi zi parameterized by theta. And what we are going to do is we are going to uh, divide and multiply this expression by, let me maybe use a different pen here, by uh, by qi zi and qi zi here, right? And this is clearly equal, right, assuming that qi zi does not vanish at any zi, right? So this is these two sort of the original um, log of this expression, right? I've omitted the outside some overall examples just to keep the notation simpler, right? Just to keep the expression simpler, right? These two are equivalent, the original sort of log likelihood and this expression. Now, if you look at it carefully, right, if I draw this line here, right, this particular uh, line here, and maybe here, then then you see the form of an expectation emerging out of it, right? So think of this log as your f function, and then what you're doing is essentially you're taking sort of expectation of this quantity, right, which you can think of as sort of your x, right? So this is of the form of f of expected value of x with respect to the distribution qi zi, right? This is your distribution of interest, and log being a concave function, now we can apply Jensen's inequality, right? And in case of concave function, this expression is greater than or equal to the expected value of fx, which in this case would be, right now, because we want to compute the expected value of fx. So this zi will come out, right? And then we will write f of x, which is nothing but log of p of xi zi parameterized by theta over qi zi, right? And into, right, because it is an expected value, p q of qi of zi, right? And this is sort of entire expression, right? This is the entire sort of expression, right? And convince yourself the RHS is nothing but expected value of this log of p of xi zi parameterized by theta divided by qi zi. and this is using Jensen's inequality. Now, this is great for us, right? This is really good for us because what we have done using this inequality uh, is the fact that we have, exactly solved our intractability problem, that we have been able to take out the sum out of the log, right? But of course, now we have this inequality coming in, right? The RHS is not exactly equal to LHS, and we will see how to deal with that in the next slide. So let me write that expression again here. So we have log of sum over Zi, P of Xi Zi, parameterized by theta over Qi Zi into Qi Zi is greater than equal to, right, uh, sum over Zi of log of P of Xi Zi parameterized by theta over Qi Zi into Qi Zi. Okay. And now the question is, um, right? In fact, if you were to sort of make it more clear, right, you could write it like this, right? And that makes it more clear. And maybe there is a bracket here also, right? So that makes it quite clear what is happening, and also how we are applying Jensen's inequality, right? So before we actually go to use this, right, and there is something that we should point out, note here, which is sort of the one last bit, is when does above become an equality, right? So we would really like to sort of answer, right, when does it become an equality? And given that log is a strictly concave function, right, above will become inequality, right? Clearly Qi Zi is some arbitrary distribution, right? So the only sort of condition, right, which is or I guess the necessary sort of condition for above to become an equality in this case would be when this f uh, um, this f function uh, is a constant function, right? And that will happen, right, if the expression inside this f of right expected f of expected value of x, right, if this x collapses to a constant function, then this would happen. And this is exactly when we have p of xi zi parameterized by theta over qi zi, right? If this sort of entire quantity becomes equal to some constant c, then the expression inside the log will be just a constant function, and the two sides will become an equality, right? And when does that happen, right? Here c is some constant, right? So which means that p of xi zi parameterized by theta is c qi zi, right? And then summing over zi, right, we get uh, uh, right, sum over zi of pxi zi theta, and then because qi zi is a distribution over zi, right, RHS is just c, right? So we get this is the value of this constant that we need, and substituting it back in this equation one, we get uh, qi zi is nothing but p xi zi parameterized by theta over c, where c is nothing but summation zi p of xi zi theta, but this quantity is nothing because we are summing over all zi's. This is the marginal distribution over xi, right? And therefore this entire expression becomes p of xi zi parameterized by theta over p of xi parameterized by theta, which is nothing but the conditional distribution of zi given xi parameterized by theta, right? And this is essentially the value of qi zi, right, for which above inequality will become an equality, right? So what have we done here, right? So what we have done here is we have sort of shown the above sort of inequality using Jensen's inequality, and we have also found, the case where this inequality becomes equality, which is exactly this qi zi for every I. This is the probability of zi given xi given the current theta, right? The theta set of parameters, right? And this will be essential for us in the next step of the algorithm. Okay, so just to sort of summarize, right, and sort of give intuition of what is going to come next, is what we have done here is that we have essentially, just writing this expression again because I'm on the next slide. So log of summation over zi of p of xi zi parameterized by theta, right, and qi zi qi zi, right? This is the expression, and remember that this was nothing but the expression of the log likelihood of the data, right? Because this qi zi was a sort of extra that we multiplied and divided by, and rest was, right now I take a sum over all examples, right? Right? So this was the log likelihood of the data, and this is greater than equal to, right, using Jensen's inequality, another quantity where we are able to take the sum out, right, of this log, and which is zi of p of xi zi parameterized by theta over qi zi into qi of zi, right? And right, let me call this as ll of ll prime theta, right? Right, so what we have done here is ll theta is greater than equal to this ll prime theta, which can be thought of as an approximation or lower bound on original likelihood, and which is hopefully something which is tractable, right? Why? Because we have moved the sum inside the log, right? In fact, I have to correct it here. There is a log here. Okay, right? And not only that, right? We also have that ll theta becomes equal to ll prime theta if we choose for all I qi zi to be exactly sort of the conditional distribution of zi xi given the current set of theta, right? So if we choose qi zi in this manner for all I, then we these two become equal, right? And as we will see in the next class, right, let me sort of give you just the intuition of what is going to come, is that is that we have this complicated sort of expression that we want to optimize, right, which is maybe something like this, and this curve represents ll theta, right? So this is a difficult to optimize function, and what we have done using Jensen's inequality is that we have constructed a lower bound to ll theta, right? And this is sort of theta, and we have constructed a lower bound to ll theta, right? So we have constructed another function which is probably more smooth than ll theta, right? Because of this sum getting out of the log. But not only that, what we have been able to do is that this lower bound touches the original function ll theta at a particular let's say theta t, uh, right, such that right, and where does it touch? It touches exactly at the point where qi zi, are these conditional distributions of pi zi given xi at right. Right, we have constructed a lower bound, and this lower bound has the property that it touches the right. This is ll prime theta, right. This lower bound has the property that it is not only the lower bound, but it also touches the original function, because this inequality becomes equality at those thetas, right, where such that right qi zi, right, or in other words, right, if we choose qi zi to be exactly the conditional distribution of zi given xi, um, given some theta, right, at those particular theta which I'm calling here theta t, right, this lower bound becomes equal to the original function, right. And in a nutshell, what we'll do is sort of we will construct this lower bound at a given set of theta parameters, right, which will be over e step, right, in the EM algorithm. So the e step will essentially will correspond to constructing this lower bound, which is figuring out qi zi's, right, and which in fact we've written the expression, and then the m step would simply correspond to to maximizing the current lower bound, right. So we'll construct this lower bound at a given theta parameters, right, and then we will, instead of maximizing the original function, we'll maximize this lower bound, and once we maximize the lower bound, then we sort of uh, will go to a new theta t plus 1, right, which is sort of the maximization of this lower bound, and construct a new sort of lower bound, which is a better approximation to the original function, right. And this process of alternating between e and m step will sort of converge the optimum of the original function, right. And I understand some things may not be entirely clear, but we'll sort of deal with this in the next class.